Okay, so welcome everyone. Welcome again to our machine learning career track. We are in our deep learning module. And for those who are watching this live and recorded, my name is Mihir Thakkar. And we are in our deep learning module in the machine learning career track at Code Hiroko. In our today's class, we'll be going over some more details about convolution networks. Yesterday, we had started about studying the basics behind how convolution neural networks work. And today we'll be using them to implement a real application. We'll be using convolution neural networks for image classification, and specifically we'll be solving a problem of malaria detection. So as you might know, malaria is an infectious disease which is very common in developing countries like India. So today we'll be using deep learning and how we could use deep learning to classify whether the cells of whether images of a cell have been infected with malaria or not. So pretty interesting application. And today we'll first go over some of the things that we have studied yesterday. We'll dive into some details, and then we'll go on to our hands-on part where we will implement this in our Google Colab notebook. All right, so let's see what we are going to go over today. First, we'll start off with a quick recap of things that we have seen yesterday. And specifically, we'll be brushing up our concepts about convolution neural networks. Then we'll also see how you could calculate the number of parameters which your convolution neural networks are using. And we'll do some calculations and quizzes around those things. We'll also see some of the classic architectures in convolution neural networks that have been groundbreaking and that have been the state of the art in a popular competition, which is called as ImageNet, which is based on the ImageNet dataset. So we'll be seeing some of the architectures that have been able to achieve the state of the art performance. And our hope will be to learn from these architectures so that the networks that we build are also, they perform really good. So, it is our hope that if these network architectures have performed good on the ImageNet dataset, it's most likely that on your dataset as well, a similar architecture would perform really well. In fact, one of the common, I would say, approaches that a lot of people take is also using these architectures as a starting point to build any other convolution neural network for your application. So we'll see some details about those going ahead. And then, of course, we'll quickly dive into our hands-on exercise where we'll use a convolution neural network to detect whether the images of a human cell have been infected with malaria or not. All right, sounds good. Any questions until now on what we have seen so far? Obviously, I'll do a quick recap of those things, but any questions before we start? Okay, if there are anything that come up during we do the quick recap, please do let me know. So yesterday we started off with the motivation behind convolution neural networks. We said that let's say when we are dealing with smaller images, something like this one, when we were dealing with the MNIST data set, where we had a 28 cross 28 times 1, which is the one channel, it's a grayscale image. So we had about 784 features over here, which is not that bad, which we can handle directly with a fully connected network as well. So if you look at the input feature size is 784, let's say we take 100 hidden units in our in our hidden layer. So the number of parameters that you will be working with will be somewhere about 784, 100, which is not that bad for a neural network, right? And if you are given a big enough data set, which something like MNIST, the chances of you overfitting are less with these number of parameters. So that is good. That's the good picture, or that's a good, I would say, the happy path, right? But what happens when in any real world sophisticated application, you might not have just these small images, but you could expect larger images as well. You expect your network to work with some larger images as well. So for example, in this case, I have a picture of a cat and I want to classify whether this is a cat or not. And maybe I have a image size of about 1000 times 1000 pixel, and it is a 3-channel image, which means it's a color image. So if you look at the number of input feature size we have, it's a large image. We have about 3 million input features over here. And if you look at, even if we take just 100 hidden units, which is really less in terms of the modern standards, but even if you take just 100 hidden units, you'll end up with 3 million times 100, which is a large number of 300 million parameters, right? So which is huge, even from today's standard, right? So that is something which is the motivation behind convolution neural networks is there a way we can extract some meaningful information from this picture before we feed it to our neural networks, right? As I said, when we are doing machine learning, you need to have this X, which is efficient representation of the problem that you are trying to solve. So if we give this directly to our neural networks, the fully connected neural network over there, the fully connected layer, in that case, we are not, it's not an efficient representation that we are trying to learn. So that's the motivation behind convolution neural networks in terms of how can we extract some meaningful features from this image without losing important information. And the answer to that was the convolution layer over here. A convolution layer would extract some low-level features from our data set, from our images, before we pass it to the fully connected layer. And the convolution layer does it using two concepts. The first one is the feature sharing, wherein the parameters of the networks that we learned are shared across different sections of the images. If you look at the images, most natural images, the features in these images, whether you are trying to learn an edge over here or an eye over here, these features can be shared in different parts of the images, right? These are not natural image. The pixels are not independent of each other. They are somehow correlated. So these features can be shared across different sections of the images. And that's the motivation. That's one way the convolution layer helps us to reduce the number of features, still give us a good enough performance. And the other thing is sparse connections between the layers, right? If you look at what we had done yesterday, when we pass the filter through different sections of images, you could look at it that the next layer is getting affected only by this section of the image, right? The next neuron, the next layer in the convolution neural network is getting affected by this region of the image only. So you could think of it as a sparse connection of layers, and each layer is not fully connected with the other layer. And that's the reason convolution neural network, this convolution layer, would have far less amount of features, right? So in any modern day network, what you would see is in the convolution layers, you would have only about 10 to 20% of the total number of parameters of the network, right? The remaining parameters still reside in this fully connected neural network. So about 80% of the parameters are still over here, but using these convolution layers, we are able to reduce the number of features that are fed over here, right? And hopefully we'll get better predictions because of this. Okay, does that make sense? Are there any questions on the motivation behind convolution neural networks and how they are set up at a higher level? Okay, so this is what we saw about the convolution operation on the intuition behind why convolution works. You saw that there was an input image which had an edge over here, right? As you could see, I'm shading off the regions, and these are the pixel intensity values of an image, and the color on the cell over here is the intensity value. So 0 is darker, 10 is more brighter, 30 is even more brighter. So that's what these numbers and the coloring code is telling you. The thing that we see over here is there is an edge, there is a feature over here, which is an edge in this image. And our job is to tell this to our future our successors in the network, the other layers in the network, that hey, I got an edge over here without more efficiently rather than using these many pixels, right? So what if we pass this through a convolution filter, right? So this is a filter or a mask, whatever you want to call it. It's a filter, mask, convolution. I think, yeah, these are the two terms that they use. So what if we pass through this a convolution filter or a mask of which has these pixel values, or these this is the kernel, right? So this is another name for it. It's a convolution kernel, right? So a lot of different names for the same thing, but the idea is, depending upon the weights that you use in this kernel, you will be able to identify different patterns. So the way this kernel is right now set up, you could see that we are setting it up to detect some abrupt changes in the vertical direction, right? So this is 1, 0, -1. So we are setting up this kernel to detect abrupt changes in the vertical direction. So that's the reason when you convolve it through this image, you're getting a highlighting a vertical edge which is getting detected over here. So one thing is that we are detecting the edge over here. As you see this, now you are highlighting this region of the output activation units over here. The other thing that you also notice is we have a 6x6 image, which is now getting reduced to a 4x4 image as well, right? So we are reducing the size of the image, or the size of the features, the activations are getting reduced as we move ahead in the network. So the question is, so if you have a grayscale image and we pass through this filter, then the image will have a black background with white outline. So I'm not sure if I get the question properly, but let me try to understand it again. If you have a grayscale image and we pass this through the filter, then the image will have a black background. The resulting image, do you mean the resulting image will have a black background with white outlines? So now this image over here, right? So don't interpret this result as also an image, okay? You can visualize it as an image, but treat them as numbers over here now. Okay, you can plot it out as an image if you want, but these are not, you shouldn't literally treat this as an image. If you want, you could plot it out and it will look, yes, it will look like, this is what it will look like. It exactly what I'm showing you over here. It's a black borders and a white, brighter edge in between. So yes, exactly what, as you said. So this is what the image will look like, and that's what I'm showing you in the image as the table as well. This is the output image. This is how it will look like. These are black borders around the top on the sides, and this is a white area, a brighter area right in the middle. Okay. Or what we are saying is, yes, we have got an edge to the future layers in the network. Okay, so two things. One is that we are detecting a feature, and two, we are also reducing the size of our activation. Right, because that was the whole purpose. As we go deeper into the network, we want fewer features, right? If we have these many, if we have large number of features over here, we want to go on decreasing them as we go deeper in the network. And here are some different parameters that you could have used in this filter, and you get different kinds of results, right? So if you have an input image like this, you convolve it with a filter like this one, you'll get some edge detection like this. If you convolve it with the filter like this one, you get a different edge detector, right? So the debate before was, what kind of numbers should we use over there? And now people realized is, rather than hard coding these numbers, it was much better if we could let the computer learn these parameters by itself, rather than just like we are training other layers of network the other weights, we could now use the backpropagation algorithm and learn the parameters for this filters as well. Right, so instead of hard coding these numbers, you would apply the same algorithm that we are using for our fully connected layers to learn the weights of this this network layer as well. Right, so that's the principal concept, or that's a revolutionary idea over here, that rather than hard coding these feature vectors, we will let the computer learn by itself, and this will be just part of our optimization objective. Does that make sense? So you would have X, you convolve it with W vector over here, and now you get some output, and then you compare it with what you actually wanted, and then you adjust your W accordingly. So we also spoke about padding because we want to make sure that our input activation size does not get reduced so much that we lose all the information. So, and also the bordering pixels we need to make sure that they are considered enough number of times. So we could add a padding around our input image to make sure that the result size is same as the input size if we want. Right, so that's one thing that we could do. The other thing that we could now change is by how many units we move this filter for every iteration. Do we move it by one block? Do we move it by 2 blocks on this image? That is something which is called as a stride of this convolution filter. And we also saw that the resulting output over here, the N out over here, would obviously depend upon the input features. The size of padding, it is 2p, because if you add a padding of 1 over here, it will get added on all the sides. So it is 2p minus the filter size. The k is the filter size. In this case, this is 3, divided by the stride, how many times you move the filter. So if you move the filter more every time, the output size will be less, plus 1, just because these things are odd, I guess. So you to adjust for that, you would add a plus 1 over here in the formula. Okay, so let's do a quick example over here just to make sure we understand this concept. So yeah, before we do the example, let's look at, if you put all these things together, how this thing would look like. So you again have, if you have an RGB image, you would have 3 channels over here. You have filter 1 with 3 channels as well. You have filter 2 with 3 channels. As I said, sometimes you want to detect horizontal edges. Maybe you want to detect vertical edge, right? And so many different things that we could have come up. And given that we have, we are learning these vectors, W's, we are learning them automatically, and we are not hard coding them. Our computer would come up with even more complex features. Maybe it is detecting an edge in 45-degree angles and so on. So we would have a lot of filters that we would put in parallel. And when you convolve them, each filter even for the RGB 3-channel image, it would just give you 1 channel output. Okay, and you stack the results of multiple filters together. So this filter convolve will give just 1 layer. It will be just 1 flat 2D surface. This will also give you 1 flat 2D surface. And you stack multiple results of multiple filters together to get a volume over here. You pass that through a ReLU activation function. Again, this is a new thing. Now people in the olden days, they did not pass the output of convolution layer through a ReLU, but now they do. So you would now you essentially get rid of all negative values from here, right? So if the input activation is less than, if it is less than 0, the output is 0. So now you get rid of all negative values over here. So if there is something like -3, that will go off, right? And everything which is above 0 just stays the same. Then you also add a bias parameter to add more flexibility to your filters parameter. So this is another parameter that you add, and this is the eventual output. So because it was we did a 3x3, we were getting a 3x3 output over here. And we had 2 filters, so we got 3x3 times 2. Okay. So let's do an example so this is more clear. So calculate the resulting volume size when an input color image of 227 times 227 is passed through 96 convolution kernels of size 11 by 11 with no padding and a stride of 4. For your convenience, I've given you the formula over here. This is the setup. We have this input image 227 cross 227, and this is the kernel which we are passing through the image. So this is a 3-channel image, 11 by 11 kernel. Again, it will be also 3-channel, but we have 96 such kernels, right? So this is one. Similarly, you will have 96 such kernels. Can you calculate the resulting volume? What will be the output dimensions of the, what will be the output dimensions when you pass this kernel through this image? Here's the formula for you to use, and let me know once you are done and what answer do you get. So Sudipto, also look at this image over here, right? So first understand that the resulting, when you have multiple filters, you'll always get more than one channel. Okay, so you'll always get more than one channel in the output. So you will have a stack of filters that you are passing through. So you'll get some depth over here. Okay, and this depth will always be equal to the number of filters that you use. Okay, so over here, how many filters are we using? We are using 96, right? So we are using 96 filters. So this number of channels will be always 96 because we are passing it through 96 filters. Okay, so let's calculate the X and the Y now. So what is the N input over here? The N input is 227 plus 2 times padding. We don't have any padding. It says no padding over here. So it is 2 times 0 minus K. And K for us is, what is K for us? The K is the kernel size, right? So which is 11, right? Divided by the stride is 4 plus 1. Right? So if you do the math over here, you would see that 227 plus 2 times 0 minus 11 times divided by 4 plus 1 will give you 55. Okay, so you would get 55 as X and Y, right? Because these two are, it's a square matrix that you would get. So 55 times 55 is the resulting height and the width of our result. And because we have 96 such filters, you will get a volume like this one, which will be 55 times 50 times 96. Okay, does that make sense? Does that make things clear on what will be the output dimensions? All right, great. Then we also saw that this was not enough, right? We are reducing the size, but if you look at really what we are interested in is we are trying to see if there is something happening in this region of image, right? We want to tell it to our next layer that, hey, there is something happening over here in this region. Hey, there is something happening in this region. So what we could do is take the maximum of values in this region of the matrix that we are getting. So essentially, if we have a 8 cross 8, in this case, this is a 4 cross 4 output volume, we could reduce it to a 2 cross 2 volume just by using something called as max pooling. Essentially, you will have a filter that you pass through this entire image and take the maximum of the values in that image. So in this case, the maximum value is 7 over here. So we took the 7 over here. In this case, the maximum is 6. So 6 comes over here and so on. Okay. So that's the pooling layer. There are no parameters associated with the learnable parameters associated with the pooling layer, right? There is nothing. All these are hyperparameters. We are not learning anything in the pooling layer. Okay. So sometimes people call the convolution layer plus the pooling layer as entire one layer of convolution. Okay, because there are no parameters to learn in the pooling layer itself. Yes, that is correct. If there are outliers or there is some noise in the image, max pooling might not give us good results. So a lot of times what you also see is people pass the input images through a blurring kernel. Okay, so they would first denoise the image using Gaussian blurring or something like that, and then they would pass it through the neural network. And also the effect of convolution as such over here. Now in that case as well, when you pass the kernel, now it is looking at a section of image and not just one one pixel itself, right? So either ways, if you come up with a different strategy, that's always good to try out. So there is no hard and fast rule saying that you have to use a max pooling or something else. If you want to try out something else, you can try it out. So putting it all together, this is what our entire convolution neural network would look like. You would have several layers of convolution, convolution plus max pool, convolution plus max pool, and so on, until you reach to a point wherein you have a reasonable amount of input features over here. So maybe around, maybe I would say 10K to 100K, maybe not 100K, but at least 50K should be good enough for you to feed it to your fully connected layers. Okay, so if you have more over here, like you have 1 million over here, you want to go down to about 10K to 100K, so that it is manageable in your fully connected network. And then you would have several layers of fully connected layer until you get your output. And most of these layers, you will use ReLU as your activation unit for non-linearity, and only in the output layer wherein you would use something like a sigmoid or your softmax, one and the same thing, right? For your for guessing your probabilities of whether that image is in that class. Okay. So let's do one more quiz over here so that it is more clear in terms of the parameters that we are talking about. So calculate the total number of trainable parameters in the following convolution neural network. So this volume size, we already did a quiz on that. So you know how to come from this to this if you are given the filter size over here, right? The next thing that I want you to understand is how to calculate the number of parameters in this layer, right? So each cell over here has some W's associated with it, right? So in each of this block, you have some W's. So this is W1, W2, W3, W4, W5, right? And we have some depth of W's over here as well. So I want to find how many W's you have in this entire network, which we are learning. Okay. So can you go ahead and try it out on how many W's will have in this convolution neural network? So, so think about now, what is the output size over here first? So actually my bad over here. We shouldn't talk, the W's are not over here. Okay. So let's come back to the drawing board. So this is the filter which is getting applied now. So it is passed through a 5x5 filter. Right. So you have a 5x5 filter over here. And the weights are actually in this filter itself. Okay, so this is a 5x5 filter and the weights are in this filter, not in the output result. Okay, so we are trying to calculate the 5x5 weights in this 5x5 filter. How many weights do we have in this entire network? So let's start off with the first one. Let me do an example and you can do the rest of things. Right, so Sudipto says 32 times 32 times 5 times 5. Okay. So as I said, now first tell me, will our weights depend upon the filter size? Will it depend upon the input size, or will it depend on the both of these things? The number of weights that we'll have, if this is a 5x5 filter and the weights are inside this W1, W2, W3, W4, W5 and so on, are the weights, the number of weights depending upon the filter size? Do they depend upon the input image size, or do they depend on both? Okay, yeah, on the filter size, right? They depend only on the filter size. And that's the beauty of it, is that however large image that you give me, I don't care. My number of trainable parameters will only depend upon the feature size or the filter size that I select. Right. So in this case, what will be the filter size? Our filter size is 5x5. So, and how many such filters do we have? Over here, we are seeing that the output size is 6. So we have 6 filters over here. There are 6 channels over here. Right. So the output should be 5 times 5. The number of parameters should be 5 times 5 times 6. Got it? So these are the number of parameters that we have in the first layer, convolution layer 1 is 5 times 5 times 6. Got it? Can you do it for the max pooling layer, the convolution layer 2 and so on? And just one more thing, we have 5 times 5 times 6, but now each of these filters also we add a bias term over here. So assuming that we have one bias term over here, we can add a +6 to it, because no, there are 6 filters. Each filter will have one bias term. So we'll have 5 times 5 times 6 plus 6 filters. Right. So here's the first result, which is we have 5 times 5 filter times 6 number of filters. We have 6 filters, and each filter has one bias term. So total 6 bias terms. Total will get 156 as the number of parameters in our first layer. So these are the number of connections. That is a different thing. We are not learning the number of connections this time. We are learning the parameters of that filter inside the convolution filter. Okay, so can you do it for the next stage? Now this 28 cross 28 cross 6 is passed through a max pooling layer. And as I had just mentioned, how many parameters, how many learnable parameters does a max pooling layer have? Are there any parameters, learnable parameters in the max pooling layer? So are these learnable parameters or they are hyperparameters? This is the filter size and the stride size. Are these learnable parameters or these are hyperparameters? Yeah, these are hyperparameters. These are not learnable parameters. So are there any learnable parameters in the pooling layer? Nope, there are no learnable parameters. So number of learnable parameters is 0 in the pooling layer. Okay, so over here, when it passes through a pooling layer of f equals to 2 and s equals to 2, the number of learnable parameters are 0. So can you do it for this stage now? When the resulting image, after you pass it through a pool, because it will get into half, right? It is a 28 cross 28 image. Now you pass it through a max pooling of 2. So you'll get 14 cross 14 now. If you have 14 cross 14 and you pass it through 16 filters, passing through 16 filters of 5 by 5, how many parameters do we have? Pass it through 16 filters of 5 by 5. How many? Yep, that is correct. It will be 5 times 5 times 16. This entire thing plus 16. Okay, because you have 16 bias terms. Each filter will have one bias term, and these are the weights of that filter. Is that correct? So max pooling or average pooling, number of parameters as 0, and then you pass it through 16 filters of 5 times 5 times 6. I'm not sure where we are getting this 6 from. So we are getting 5 times 5 times 16, I said. So I guess this should be 5 times 5 times 16. I'm not sure if this is correct. Okay, because we have 16 such filters. Each filter is 5 cross 5. Each filter is 5 cross 5. We have 16 number of filters. So it should be 5 times 5 times 16. Okay, plus 16 weights and whatever you get as the answer. Okay, I'm not sure if this is correct over here. Okay, so after we are done with that, the next thing that we do is again max pooling. The number of learnable parameters will be 0. Now this entire thing now is flattened. Okay, so this entire thing is now flattened and fed to a fully connected layer. Okay, so we have this 5 times 5 times 16 because there is a max pooling over here, right? So this is 10 by 10 gets halved into 5 times 5 times 16 with max pooling. And then you feed it to 120 hidden units. So with 120 hidden units, you would have 400 times 120 connections because this is 400, right? So you have 400 x1, x2, and you would have 400 over here until 400. And each X is connected to each hidden unit over here, right? So it's a densely connected network. So you would get 400 times 120 parameters plus the bias terms, which is 120, and whatever you get as the number of parameters over here. Does that make sense for the fully connected layer? So as you see, as we are going deeper into the network, the size of our volume is decreasing, right? So this was a bigger volume, 28 cross 28 cross 6. Then we are left with now 5 cross 5 cross 16. And a number of parameters is, will be maximum in the fully connected layers, right? Over here we have about 1,500. This is 156, right? So in less than around 1,000 parameters. But in the first fully connected layer itself, we have 48K parameters, right? Which is huge. So in a convolution layers, we'll usually have less number of parameters, but in a fully connected layer, you will obviously have a huge number of parameters. Okay, does that make sense? And then that is passed through another fully connected layer of 84. Can you do the calculation of this? So there are 120 hidden units over here, and there are another 84 units over here. So can you tell me for the last time, how many parameters will we have? Both of these are fully connected. 120 units to 84 units. How many parameters will you have? Yeah, 120 times 84 plus 84. So 120 times 84 plus 84, because each of this hidden unit also has some bias terms, right? So 84 units has 84 bias terms. So plus 84 over here, and this 120 connections over here, each of that is connected to the next network over here. So we have 120 times 84 plus 84 parameters. And that is passed through the output softmax layer, which has 10 output terms, right? So the final, I would say in the last layer as well, you would have over here, you have 84. So you are at 84 times 10 number of output plus 10, because each of this will also have some bias associated with in the final layer over here, right? So in the last layer, you would have 84 times 10 plus 10 parameters to learn. Okay. Is that clear on how to calculate the number of parameters in any convolution neural network? Okay, great. So one trend that you should notice is about 80% of your parameters will be in the fully connected layer. Not 80K, I want to say 80% of the parameters, and about only 5 to 10% or 10 to 20% you should expect over here. Okay, so 10 to 20% should be over here. I'm giving you these intuitions because going ahead, we'll be designing our own convolution neural network, right? So as they say, there is no right or wrong design, there is only good or bad designs, right? So these things we are going to design by ourselves. In that case, we need to look at some examples on how people have done it before. So this example that we did is from a classic example or a classic neural network, which is called LeNet 5, which was published back in 1998. And it still serves as inspiration for a lot of modern neural networks, and the architecture pretty much remains the same. They draw ideas from this particular architecture that we just came up with. So when we analyzed it, we also went through the math behind it. Now that helps us. We thought a lot about this, right? Rather than just seeing LeNet 5, we did some math behind it. So we now have a better feel on how this network was designed. Okay, does that make sense on why did we do this example? This is in fact a classic example of a neural network architecture, which was used for the digit recognition challenge. Not the challenge, but the digit recognition problem. Back in the olden days, banks wanted to do some sort of an OCR on the checks, right? And they used this LeNet architecture to build their OCR engines. Okay. So when to use CNNs? Well, it should be a bit obvious to you by now, is that whenever we have spatial correlations between the features, right? That's a good use case for CNN then. And when do we have spatial correlations? Can you think some examples on when we have, what kind of data would have some spatial correlation between the features? Yeah, obviously images, we just saw it, right? Pixels of image are spatially correlated with each other. So pixels of images, can you think of some other examples where uh, you would see some spatial correlations? Yeah, images, videos, all come in the same category. So with video, we are also adding an element of time to it, right? Because it's a three-dimensional, not three, but even more dimensions of data now. So what else? What might have some correlation between subsequent features? So words in a document of text, even they would have some correlation. We don't use random words in a language. When you frame certain sentence in a language, there is some structure to it. No, something like you would have a noun, verb, then some adjective and so on. So there is some structure to any language as well. Is that true? In the structure is not as I would say common, or it's not that strong correlation like you would have for images, but there is still some structure for sure. And also, whenever you are dealing with time series data, it is often the case that there are subsequent timestamps are correlated with each other, right? When things occur in a pattern of a series of a time steps, in that case, you might want to try it out with a convolution neural network. Although these two are not widely used, the best example, or CNNs have been deployed as state-of-the-art networks for images and videos. Okay, so most likely when you have images and videos, CNN is your go-to tool. For others, you might try it out, but they are not so popular as well. Okay. So let's look at some examples of CNN architectures. I will now skim through it quickly because we need to move into our hands-on exercise as well. But let's just look at some examples of CNNs. So LeanNet 5, as I said, we just did an example on the same architecture. We calculated the number of parameters in LeanNet 5. So this was published back in 1998, and the total number of parameters, if you add all the parameters up that we did, would come to about 60,000 parameters in the total learnable parameters in the network. So almost for like say 10 to 12 years, I see that there wasn't any significant improvement in neural networks, right? Thing that got attention of most people is this paper, or this network from 2012, this architecture which was called from AlexNet, right? So this is AlexNet from 2012. They won the ImageNet challenge by reducing the error from 26% to 15.3%, right? So back then in 2012, when in 2010 and 11, when the error rates were more than 26% on the ImageNet data, these guys suddenly came in and dropped more than half the error rate on the ImageNet competition, right? Which was significant. The second entry had in 2012, the second entry, which was not a convolution neural network, had an error rate around 26%. And these guys who were at the first place, they were far more ahead than the person on the second place as well. They got an error down from 26% to 15.3%, which was significant. And that is what caught attention of the research community is that, hey, these things tend to work better. These people have showed why these that you could actually use neural networks for important image recognition task as well. So before this, people did not take it that seriously. Before this happened in 2012, CNNs were not that widely used for image recognition, but this paper and this network changed everything. And also I'm highlighting this guy over here. So this is the same person who also recently won the Turing's award from Google for their work in deep learning, right? So significant improvement over the previous networks. It had a similar architecture to that of LeNet. You could see that it is still similar. This is also an example that we solved right now. This is the first example that we solved on. We calculated this 55 cross 55 cross 96. So you know how to calculate these numbers now, right? And as you see over here, it has pretty much the same kind of architecture. The only thing is they are using some bigger kernels, right? So they have 11 cross 11 kernels, and they have more number of max pool layers, and then they have fully connected layer. So overall, I think they have lot of parameters. Still, they have a lot of parameters over here in the network that they are training. So GoogleNet, which came, so over here in AlexNet, you would see that there are 60 million parameters that they are training on. Okay, so they were using a bunch of GPUs. They did some parallel processing, and they were training on multiple machines and so on. And they were training 60 million parameters for this competition. So then came GoogleNet or Inception in 2014. Instead of using large convolution filters, they reduced the filter size, right? So they had very smaller filters of 3 cross 3 and 5 cross 5, even smaller filters, but they had a deep network architecture, right? So they have a lot of layers. They have 22 layer deep architecture. They reduce the number of parameters from 60 million to 4 million. Okay, they reduce the number of parameters, and that made it easier for it made it faster as well. Okay, so something for you to look at. So the trend today is that you go for deeper networks with smaller filters. So just showing you some state-of-the-art performances on the ImageNet competition. I think the ImageNet competition is not no longer active. It was active between 2010 and 17, I guess, but now it's not active anymore. So this one over here, now this ResNet also caught a lot of attention because now it is 152 layers deep. You can see the performance. So you need to read this graph from left to right, which I wish they did not do that, right to left, but read it from this side. So you see the AlexNet is right over here with 8 layers, and this is the error rate that they had got. And now significantly going ahead, now this GoogleNet over here and this ImageNet over here or ResNet over here has an error performance. The performance over here is better than human, right? So this is superhuman recognition abilities. So even humans can't perform this well on the ImageNet data that this network is able to do. And of course, they have used a lot of parameters. They are using 60 million parameters over here in the ResNet CNN. Okay. So have a look at this graph and let me know if you have any questions on the network architectures that we have seen. All right, great. So let's move on to our hands-on exercise. Let's move on to the Google Colab. So if you don't have an Google Colab, I mean, I'm sure you would have a Google account at least. So let's move on to colab.google.com. So you could go over here, say colab.research.google.com. Let me just paste it over here. Once you are on this site, log in with the account that you want to work with. And I'm gonna say, let me know once you see a page like this first, okay? Right, so once you see a screen like this, let's go ahead and create a new Jupyter notebook. So I said a new Python notebook over here, and I see an untitled notebook like this one. So let's go ahead and rename our notebook first. So I'm going to say Malaria Detection CNN. Okay, so do that. And the next thing that I want to make sure is that we also want to use the main reason that we switch from Azure Notebooks to Google Colab is to be able to use the GPUs that they have, right? So make sure that you go to runtime over here and say change runtime type to a GPU. Okay, so that will make sure that while learning, while we are doing a training, we use the GPUs which are available. Okay, so hit save over here. That should reset your runtime now. So just wait for a second. If you go to files over here, it would say connecting to a runtime as well. And let me know once you have connected your runtime and you switch to the GPU over here. So on the runtime type, you should see, you'd see a GPU over here, right? So I just switched, so I'm just gonna say cancel. Let me know once you have switched your runtime to use a GPU. All right, great. So the next thing that we are going to do is also import the data set that we are going to work on. So let me give you the two files that we have uploaded onto our servers for us to train. So let me go ahead and paste this, the curl command to you. So this is the place where we have the two files. So go ahead and paste it in your Colab and execute the cell, shift enter. So this is the place where we have our training and test data sets for malaria detection. All right, so once you see that these both have been downloaded, no 100%, you can also go to your, on the left hand side, you can go to files and hit refresh over here. And that would make sure that you see the test and train.csv files. Okay. So generally these images have been available online in image form. But what I have done is, for our convenience in the class today, I've converted them to CSV files so that it is easier for us to work with. A lot of times, people would spend several hours just loading the data set into their Jupyter notebooks and so on. I have a script which I'll upload on our GitHub repo as well, and you could find it in the video description on how did we convert the images to these CSV files. Okay. But the purpose of the class today is to understand the working of the convolution neural networks and not really image pre-processing. So I don't want to dive too much deep into how did we convert them. You could see all our past videos on SVM as well, where we did the step in the digit recognizer project as well. We converted the images to CSV file and so on. So we have done this several times, so nothing new. But just have a look at the script which is given in the description as well if you would want to know how did we generate these CSV files. Okay, so having said that, let's see what do we have in our training and test data files. So what I'm going to do is use our favorite package, which is pandas. So Sudipto, let's just look at what is inside the data and you will know what do we have. Okay, whether it's a CSV, whether it's a color image or an it's a grayscale image, you will find out. So we'll use our favorite package pandas and load these CSV files. Let's go ahead and do that. So let me make sure that you are able to see my screen properly. And it's big enough. Okay, so import pandas as PD. And then we could say, I'm going to say train data frame instead of no. So I'm going to say train pd.read_CSV. I'm going to say train.csv. And I'm going to say test equals to pd.read_CSV. Test.csv. Okay. Let's run this. So it might take some time. Okay, so once we have loaded our training and test data, let's look what is inside that. So let's say if I want to say train.head over here, what do I get? Okay, so it looks like we have the label, whether that image of the cell has been infected, which means parasitized or not. And then we have pixels from pixel 0 to all the way to pixel to 499. So we have 2500 pixels of each image in one row of our cell, right? So if we say train.tail over here, you would see that we also have the uninfected images. So in the start of that file, we have the infected images, and towards the end, we have the uninfected images. Okay, so we can also say train.describe over here, I guess. That will give us a sense of how many classes do we have. Okay, so seems like the pixel 0 over here has a minimum intensity of 0 and the maximum of 174, right? So everything it seems between. So can you tell me now whether it's an grayscale image or a color image that we have just by looking at the data now? Yeah, it's a grayscale image because we don't have 3 channels as such, right? So we don't have 3 channels. We just have pixel 0 to 2500. So it means it's a 50 cross 50 image. Do you agree on that? There are 2500 pixels. and there are 50 cross, it's a 50 cross 50 image, and each now value of a pixel is ranging from between 0 to somewhere around 200, it looks like. So it's a grayscale image which has pixel intensities between 0 to 255. Okay. All right, so let's also plot it out so that it is more clear on how each training image looks like, because we would rather have it visualize it first rather than just trusting our instincts over there. Right, so let's try to plot it out and see. First, try it out yourself. Can you try to plot the image? So can you plot the first data frame over there? Or the first value from the data frame, first row from the data frame? Or let's just do one thing. First, let's split it up into X and Y's like we usually do, and then we'll visualize it. Okay, is that okay? First, let me just move it up. Let's come over here. Let's come over here and say train.head over here. First, let's split it up. So now this is something that we have done before as well. We'll use the same technique that we usually do. First, we'll now this time understand that we have the training and test in the different data frames. Usually we have everything together and then we use the train test split. So this time we have them in different files. So first I'm going to split the xtrain and xtest. So here's how the xtrain should look like. I'm going to take the training data. So you're going to take the training data, xtrain should be when I say train.drop, right? We are going to drop the label out of it. Is that correct? So if I drop the label from here, I'll get all the pixels from 0 to 255. So xtrain should be train.drop label, and we could say access as 0. Now this is something that we have done before, right? We want to make sure that we drop it from, this should be 0, or I think it should be 1, right? Because we're dropping the column over here. Right, so xtrain should be this, and then if I want to say ytrain over here, this should be simply train of label. Is that correct? Okay, and one more thing that I'm going to do is I'm going to work with, instead of working with the data frame, I want to work with the NumPy arrays, because it's much more easier for me to then feed it to our TensorFlow network. So we'll convert this to NumPy arrays by saying values over here. Okay, so this is dot values. This will convert it to a NumPy array, and that will help us a lot. Okay, so similarly, we can do it for xtest as well. Okay, so we did it for xtrain, ytrain. Can we do it for xtest and ytest as well? So we can do it for xtest and ytest as well. So this should be from test.drop and test.labels. Okay, so okay. So let's see what is the shape of our training and test data points. So if I say xtrain.shape and I say ytrain.shape, So we have 22,046 training samples, and we have 2,500 features, right? And we have again 22,000 labels over here as well. Okay, and X test. Let's see what do we have there. X test.shape and Y test.shape. Now they should have similar numbers over there. Okay, 2,500 again and 5,000 test samples. Okay. So let me know once you have done. You have separated out your X train, X test, Y train, and Y test. All right. So the next thing that we are going to do is let's just visualize our data. So I'm going to use my matplotlib to do that. So I'm going to say import matplotlib dot pyplot as plt. Now again, you have used the same module several times before. And then let's say if you want to visualize at index equals to sum. And so let's say I want to visualize at index 2000. Then I could say plot.imshow. I'm going to say xtrain at that index, right? And then because I want to show this as an image, I should say reshape to 50 cross 50 because it will be a 2,500 pixels wide. It is a flat image. I want to reshape to an image. So I want to make it a grid so I can plot it as a 50 cross 50 image. And then I'm going to say CMap equals to gray because it's a grayscale image. Okay. And let's see what do we get. Okay. So seems like we are now plotting this image. So this is the cell, the image of the cell, which we don't know what this is, if this is infected or not. So let's also print out the Y test associated or Y train associated with the same index, right? And let's see what do we get. Okay, so this is the parasitized image. So this is how a parasitized or infected cell of malaria looks like. Infected by malaria looks like you have some spots in the cell, and that's the reason it looks like you have been infected over here. Okay, and let's say if we want to see what an uninfected image looks like, so let's say if I say 20,000 over here, so this is what an uninfected image looks like. There is some variations, but more overall no, it doesn't look like a spot over there, right? So if you look like 20 to 100, so we run out of images over there. So 20,001 maybe. Okay, so it's overall looks like a clean cell, then it's uninfected. But if you have something like, if you have malaria, you would have some spots like these, which means you have been infected or no, there is some parasite over here. Okay, so our job will be to automatically do this. Right now we are doing it. Right now we are doing this manually. We are eyeing it, and just by looking at the cell, we can say this, yes, it looks like there is some infection over here, but we want our neural network to do this as well. Okay, so try it out and let me know if you understand how this training data is laid out. Let me know once you are done. Okay, so once we are done with this, let's try to do some pre-processing on our features over here. We know that to feed it to our convolution neural network, convolution neural network would generally take a 2D dimension, two-dimensional image as an input. So for our Keras API to work properly, we also need to reshape our data to a 50 cross 50 image. So right now our XTrain, for plotting purpose as well, we had to reshape. So let's do it now permanently to our XTrain over here. So what we'll do is reshape our XTrain to a 50 cross 50 dimension. So XTrain, I'm going to say is XTrain.reshape. The first dimension would be same as whatever XTrain is right now. So I'm going to say train.shape of 0. Right. So whatever, how many number of data sets or data you have, keep that as is. So if you have 22,000 images, this number is still 22,000, right? So that remains the same. And then you would have train.shape of 0, then we could say 50 cross 50 over here, right? Okay, so, and the next thing that you also want to do is also say not as type float 32, just to make sure that these are treated as floating point numbers and not integers. And then I'm going to say xtrain equals to xtrain divided by 255.0. Okay, so can you tell me why am I doing dividing by 255.0? So I'm normalizing all the values for xtrain. The maximum value is 255.0 for any grayscale image. So I want all the values between 0 and 1. Okay, does that make sense? Okay, so let's do it for X test as well. Can you go ahead and do it for X test as well? So do it for X test as well, because the same thing that we do for X train, we need to do it for X test as well. So just one thing that we need to make sure over here is also say 50 times 50 times 1 over here, which we mean is that we have one channel image, right? So if you're feeding in 3 channel image, an RGB image, you will have 3, but we have a grayscale image. So we just have one channel over here. So just make sure you say 50 times 50 times 1 over here. Okay. And then X train is same thing. So let's do the same for X test as well. I'm just going to change this to X test now. Okay, so looks good to me. So we have some problem over here, it seems. So yeah, this should be test.shape, right? Okay. All right, so the last pre-processing step that we are going to do, if you look at the Y train over here, when we plotted Y train of index, we are seeing parasitized as a string over here, right? We don't want the strings, we can't feed it to our neural network, or any model as such. We want to feed them as numbers, or no, the index of that class. So you want to say either class 0, class 1. So you want number 0, 1, 2, 3, and so on. So we want to convert this string, these categorical variable to numbers over here. So we'll use scikit-learn. I'm trying to use packages that you guys are already familiar with, rather than trying to do something with TensorFlow or Keras. So let's use scikit-learn, something that we are already familiar with, and convert these to binary labels, either 0 or 1. Okay, so I'm going to use scikit-learn to do that now. Again, as you see, there are some pre-processing steps that are involved in any project. I've tried to keep it as little as we can, so that we can focus more on the convolution neural network part of it. But still, there are some steps that you have to do in any project, and I did not want to skip them over here. Okay. So I'm going to create a binary label binarizer. So first of all, I want you to try to do that as well. So try to use scikit-learn pre-processing package and convert this label over here, parasitized or uninfected, to it. Our white train and white test should contain only 0 or 1. Okay, so if it is parasitized, we should have 0 or either 1. So feel free to any method that you want. If you want to do it in the data frame itself, there is a way to do it in the data frame as well. If you want to do it over here, do it over here. If you want to do it in NumPy, do it over there. Feel free to use any method. The end result should be, instead of parasitized, we should have 0. And if it is uninfected, we should have 1. Okay. Do you get the objective of what we want to do with white train and white test? So unless we label encoded, no, we won't be able to feed it to any model, okay? Because you can't pass them as a tree over there. Well, I'm not sure if that is true to any kind of model. When you are feeding in, if you don't do it, no, there is no way for your model to understand those strings unless there is someone who has already done it for you. If we have that inside our data set itself, well, then we need to check it out. Okay, so I'm not sure if that is going to be true. I'm not sure if we did that exercise over here. Did you try out any stuff from your side? Well, yeah, if you are uh, building that model from scratch, and then if you're doing some if else statement, then yes, maybe. Right, so let me do it as well over here. What I'm going to use is something called as a label binarizer from the scikit-learn package. And there are other ways, as I said, you could do it in pandas as well. I'm going to use the label binarizer from the scikit-learn pre-processing module. Okay, so I'm going to say label binarizer is processing dot label binarizer. Then I could say white train is equal to lb.fit transform my white train. And similarly for white test as well. Okay, so if we say white train of 0 now, as you see, we have element 0 over here, right? So instead of parasitized and uninfected, now we have 0 and 1 over here, right? So we have label encoded our categorical variable. Okay, so if I have to summarize all the operations that we did, so let me just print out the shapes of print xtrain shape. So X train and Y train, Y test should be similar, right? So if you have these as your shapes, then you're good to go. We have 22,000 samples. Each should be 50 cross 50 cross 1. And we have Now one dimensional label encoded training labels over here. Okay, so print this out and make sure that you have your dimensions for X train, Y train correct. Right, so let me know once you have done and you have verified that your X train, Y train, and your are of the same dimensions as that I have. All right, so here's the architecture that we're gonna use. Let me know once you have completed the uh, pre-processing on the training and test data sets. Or let me know if you need some more time. All right, so this is the architecture that we are gonna use today. Okay, and as I said, there is no right or wrong answers to this. And now you might have realized that there are so many hyperparameters that were involved. If you look over here in all the architectures that we have seen, all these are the hyperparameters, right? How to select the kernel size over here, how many kernels to choose, and all these are hyperparameters that we are setting. So there is no right or wrong answer to it. One trend that we see is, going ahead, we want to use smaller filter size of maybe 3x3 and 5x5. That is something that we have seen so far. And the other thing that we see is, we want to reduce the number of parameters as we go deeper in the network, so that in our fully connected layer, we don't have large number of connections. So maybe we want to get from a bigger image to a smaller activation units over here. Okay, so that will be a strategy. There is no right or wrong answer to it, but this is how I'm going to design my network today. Feel free to try out different kernel sizes, different depths of layers, and as many different things that you would like to get better performance. Okay, so here's what we are going to do. What is our input image size? So how big is our image right now? We have a 50x50 image. Do we have 3 channels or 1 channel? We have just 1 channel because it's a grayscale image, right? So we have 1 channel image that we are going to feed in, and we are going to feed it to a convolution filter of size. We'll start off with a convolution filter of size 3x3. Okay, so I'm going to stick with a 3x3 filter for my entire network. I'm going to use a small filter size of 3x3, and what I'm going to do is use a ReLU activation, because we want to make sure that in olden days people used to use sigmoid, but now we use ReLU for our activation function. And the other thing that we are going to do is, once we have passed this, we'll get some lower volume, right? We'll get some volume over here. Now let's not go too much into the depth of now what will be the volume size, but we're going to start with 16 filters at first. Okay, so what will be the depth of this filters over here? We'll have 16 filters. Okay, so we know how to calculate 50x50. What will be the volume size over here? It will be definitely less than the original feature size. Okay, once we do that, the next thing that we will do is, this is our convolution layer 1. We'll pass it through a max pooling layer. We'll do a max pooling over here, and we'll do a max pooling of stride 2. Okay, so whatever this dimension it will be, it will reduce by half, right? So if in case we are getting something 28 over here, 28x28, this will become 14x14. Okay, I'm not sure what the exact dimensions of this square are going to be, but no, that will be the case. Okay, we'll pass it through max pooling, and we'll do one more layer of convolution. And that would also give us even deeper volumes, right? I'm doing a bad job at this, so let me just make sure I do it properly. Okay, we are not sure what is this number, but we'll half the volume by using max pooling. Then we'll use filter again of size 3x3 filters, and then we'll use this time we'll use 32 filters. Okay, and that would make us go even deeper, right? So we'll have smaller size now, but this will be even more deep. Okay, again max pool, and another convolution of 3x3, and this time we'll use 64 filters. So this will be even smaller and wider network. Not wider network, but we'll have more channels. Okay, So we have 64 channels over here now. This entire thing will pass it through our fully connected layer. We'll pass it through FC1 and to our softmax output layer now. Right, so this will be output layer. This will be our hidden layer. Okay, because we just have either malaria or not malaria, we just have either 0 or 1. 0 in our case is parasitized, and 1 is uninfected. Okay, so does everyone understand the network architecture that we are going to build next? At some points, I'm also going to use a dropout probability. I'm going to use a dropout of 0.2 over here and a dropout of 0.5 over here. Can someone tell me why do we use a dropout? Have we seen this before in our last class? With dropout, we are hoping to get reduce the overfitting, right? So we are hoping to reduce overfit using our dropout. Okay, and yesterday we saw how dropout could result in a new architecture every time we build our neural networks, and hoping that the ensemble of those different networks will give us much more better result. Okay, so this is what we are going to build in TensorFlow Keras API. Okay, so we'll be using the Keras API, but using the TensorFlow backend. Okay, so we'll build this in the next few minutes. So let me go ahead and do that. And let me, while I write that code, let me know if you have any questions, because most of it would be pretty obvious if you understand how this network architecture is laid out. Writing that in code, it's almost like a pseudo code over there. So let me go ahead and write it out and ask me if you have any other questions. Okay. So the first thing that we want to do is also import TensorFlow and the related APIs. So what I'm going to do is just give you the code for now for importing all the layers that we are going to use. Okay, so we are going to use all these layers. Yes, we can have more, as many hidden layers as we want. It's just that a number of parameters will go on increasing. Okay, so go ahead and import this, paste this code in your Jupyter notebook. It is pretty straightforward. I'm just importing TensorFlow and all the related layers from TensorFlow and Keras that we are going to use. So first I'm creating a sequential model. I'm going to say model equals to sequential model, and then we'll add one layer after the other, just like we saw in the PowerPoint slide over there. So I'm going to first add model dot add a convolution 2D layer. First thing, we're going to add 16 filters. So I'm going to say filters as 16. The kernel size of each filter, I'm going to keep it 3 by 3. I'm going to use the padding as same. Can you recollect what does padding equals to same mean? So there are two types of padding terminologies, padding as same and padding as valid. When you say same padding, which means you want the output to be same as the input size, and that the number of padding that you should add around your input image. Right? If you say padding as valid, that means your output of the convolution will have a reduced size. Okay, so padding as same, and then we're going to say activation is ReLU over here, which is the rectified linear unit, and we need to say the input shape that we are going to pass to this layer, which is 50 cross 50 image with one channel, right? It's a grayscale image with one channel. So I'm going to say 50 cross 50.1, and that's our first convolution layer. The next thing that we are going to add is the max pool layer, right? The max pool layer doesn't have any learnable parameters, but it will help us reduce the size of our activation by half. So we are going to use the max pool over here. We're going to say max pool, max pooling (2D). I'm going to say pool size of 2 over here. That will reduce our dimension by half. Right, and once you have done this, let's just copy this 2 more times. Okay, so I'm just gonna copy it, paste once and twice. Now the next time I'm gonna use, instead of 16 filters, let's use 32 filters and 64 filters then. Kernel size, I'll keep it as 3. If you want, you could try to increase the kernel size, but that's not a really good idea. What we have seen in recent days, as you saw, was with GoogleNet, they use smaller filters, but more deeper networks, right? So I'm going to stick with that, the same kernel size for all my networks, and padding size, I'm going to keep it same. I don't need any input shape over here, right? Because that TensorFlow will calculate for me. I don't have to do that. Again, there is no need for input shape over here. Okay, so once I copy pasted it 3 times, then I'm gonna add a dropout, as I said, model.dropout with a dropout probability of 0.2. That will help us reduce some overfitting in our network. And then we'll flatten this, because remember, you have this 50 cross 50 cross 1 dimensions which are going on. If you want to feed it to your fully connected network, right over here, when you want to pass it from this volume, you have to flatten this, right? So there is a volume over here with 64 channels. You want to flatten this to a single dimension, all in one row, just all in one vector, right? So this model.flatten will do that. Or actually you should say model.add flatten. Okay. Once we have flattened our inputs, then we could add our one hidden layer and one output layer, right? So we have one hidden layer over here. This is the one hidden layer, and this is the one output layer, which is a single neuron as such over here. So I'm going to say model dot add a dense layer, which is the fully connected layer. I'm going to use 200 hidden units. You can also increase this number of hidden units that you have, but I'm going to stick with 200 hidden units. As I said, there is no right or wrong answer to a design. It's a design. You could only have a good or a bad design. The idea should be that you need to make sure that you don't have that many parameters that you are overfitting in your network. Okay. I'm going to use activation as ReLU. And then I'm gonna do one more round of dropout over here, but this time I'm gonna use probability of 0.5. Now again, as I said, you could tweak these numbers and see if you get different better results. This is the last output layer, model.dense. There are two possible outputs, which is either 0 or 1. And the activation, for the last unit, we always use the sigmoid or the softmax, right? And then let's print out the summary of whatever we have done until now so that we can see the graph that we have created. Okay, let's see if we have made any spelling mistakes. So we have some mistake over here, which is max pooling 2D is not defined. So let's make sure that this is this guy. Max pooling 2D, max pooling 2D. Model is not defined. Okay, so this has to be smaller caps. Activation is another spelling mistake that we have made over here. Where is it? On the line 15 after ReLU over here, this guy. Oh, I see. So you need to say this is part of this model.dense activation as ReLU, model.dense to activation as softmax over here. Okay, so we created the model now. There are some spelling mistakes that I made and some typos, but this is what the code should look like now. Okay, and this is the summary of the model that we have created. Let me also paste it in the chat box so that it is easier for you to compare. All right, great. So if you look at the structure that we have created, now as we expect in the convolution layers, we have less number of parameters. Uh, and as soon as we move on to our dense layers, we have about 461,000 parameters over here, right? And that's where we would expect that most of our parameters will be in our fully connected layer and not in the convolution layer. We have some in the max pooling layer, as I said, there are no learnable parameters. Uh, how to calculate the number of parameters in these layers, we have already seen that. Okay, so I hope you have a good sense of how this network is laid out now. The last thing which is left, and we have about 484,000 parameters that we are going to learn today, okay, in for this application. All right, so let's go ahead and do the last few things, which is pretty simple now. We have done the most of the hard work. The only thing left is to now compile the model and then fit it using the model.fit. So I'm going to say model.compile now, which will actually create those connections. I'm going to say loss as a categorical cross entropy optimizer as Adam. We have seen this in our class in the first TensorFlow class. There are some other options which are available as well. All these are hyperparameters that you select. There is no rule which says that you need to use a stochastic gradient descent optimizer or an Adam optimizer. It's up to you for you to try out. So one thing that we will have to do, I guess, is to make sure that we'll have to convert this to something like sparse categorical entropy, because the white train that we have used is not in the format that this method is going to take. Okay, so we'll see, but let's just remember that we'll have to change this. I guess we'll have to change that to something like a sparse categorical entropy. So model.fit, I'm going to pass the X train, the Y train. I'm going to keep the batch size, again, another hyperparameter that you could tune, as 50 images at one time. We are going to feed it to a network for learning. And epochs, how many times I want to run the stochastic gradient descent, I'm going to run it 20 times. I'm going to say verbose as 1 so that I can see what is happening. Okay. And as I expected, we need to use the sparse categorical entropy loss because of the format we have the Y train. Okay, if you change it to something else, then we can use the categorical entropy. You might have to use something from keras.preprocessing to convert it. So right now the Y train is like this. You have Y train like this. What the categorical cross entropy loss expects is to have something like 0, 1. Okay. Again, it's just a matter of formatting. But if we have just 0 over here, we could use the other type of loss function over here, which is the sparse categorical entropy loss. So I'm just going to put that over here and then compile model.fit. So there is something metric is something wrong over here. This is metrics. Metrics is accuracy. Okay, so now as you see, we are training now. So not so good signs though, because our accuracy is not increasing over here. Let me see if we convert this thing, actually, instead of using the sparse categorical entropy, this is not a good sign. Okay, as we are increasing the epochs, we are not getting any better results. So my guess is that we are doing something wrong with the, instead of using the sparse categorical entropy, that is not a good thing to do. Okay, so my guess is we'll have to convert this to, we'll have to convert this to the, we'll have to convert the y train and y test. Okay, so let's go up and we'll convert the y train and y test to the format that it is expecting. So here's the code that I'm adding. Well, it's good that if you are getting that as well, but let's see, let me also run again. So if I run for the entire epoch, let me see what do we get. I thought it's not a good sign right now. If we are not increasing the, we're not getting better performance. Let's see. So I compile it again and running it with the sparse categorical entropy loss. Sometimes it's also that, you know, the initial weights that you select, that might also affect your performance. But for me, it's not good signs over here. For some reason, my accuracy is not going above 50%. Are you using the sparse categorical entropy, or which loss are you using? And also do it on your validation data. So you could, so for me, we are not able to get a good accuracy score over here. So I'm going to try it out with another loss, which is the categorical entropy loss, if that works for me. And for that, I'll have to convert my Y train So I've converted my Y train to categorical variables. If you do this, you'll see that you have 2 over here, because you have the Y train as 0 and 1, which is in a vector form. Let me run and compile everything again. So created a new model again. Model.compile, model.fit. Nope, for some reason, even this is not working for me. So maybe I'm doing some other silly mistake somewhere else. Not sure. So it's good that you are able to get the 95-99% accuracy, but I can't figure out where I have done something wrong. There is something wrong that I'm doing for sure. So xtrain, xtest. We have ytrain, ytest. Okay, let's run the whole code again. So let's stop this guy and let's say run all. Download the test and everything again. Okay, so seems like there was something wrong with the uh, variables or something wrong with that. So I ran the entire code and now we are getting better results now. So as you see, with each epoch now, we are increasing the accuracy score now. Eventually, up to 20 epochs, yeah, it won't be exactly the same because of the initial weights, right? Our stochastic gradient descent algorithm, we are never guaranteed that we'll reach the global optima. The initial weights, if they are random, will start off at random points. Yep, it is pretty much random. Okay, so with even 12 epochs over here, we are getting about 96% accuracy, which is really good. But this is our training accuracy, okay? This is not the same as our test accuracy. So don't get fooled by that. We need to make sure that we evaluate our model on the test data. So let's evaluate our model on the test data. So I'm going to say predictions equals to model dot evaluate. X test, Y test. Okay. And let's run this now. Now this will evaluate our model on the test data. And it has completed. So our test accuracy is actually about 95%. Okay, which is not so bad for any accurate for any classification task. Okay, so we also have a video on doing the same task with SVM. So have a look it up on Google or on YouTube. So check it out. Over there, we were getting an accuracy of about 90% with feature engineering. So we were extracting some features, but some in this one, we are just feeding in the raw pixels and our neural network was able to learn. So we did not tune a lot of hyperparameters. If we sit over there and add a lot of more deeper networks and tune some hyperparameters, we'll be able to get a much better accuracy as well, even better than this. But 95.5 is not at all bad for any classification task. Okay. All right. So also, if you want to visualize it, let's just visualize the results in terms of if how well are we doing. So I'm just gonna take any, let's say if I take index as 100 over here, and I want to say plot.imshow. I want to see X test. How was the image looking like? So I'm gonna say X test of index. Again, just do a reshape over here of 50 cross 50. And CMAP equals to gray. So this is a test image. Let's see if we can plot this. Okay, so this is the test image of an infected image, right? So this is an infected image for sure. Let me also make sure that we print that label. So print actual Y test of index. So it is 1 comma 0, which means the first class, which was the parasitized class, is 1. That's how we are label encoded this thing. So this is parasitized. This means this is parasitized. And let's print our prediction. So I'm going to say print model.predict. Okay. Do we really need the np.array over here? Let's see. Nope. I guess, or what if we did this? Yeah. So as you see over here, for 100, maybe this is not so clear, but if I say 120, so this 9.99, our probability of that it is class 1, this is 9, and this is 2.e raised to something which is much smaller, right? So we are going to predict that this is from class 1, right? So if this is, I guess 2000, which means this is this is still infected image. Let's say 4000. This is uninfected image now. For uninfected image, you see, now this is 0.63. Now this is actually a misclassified image. We are predicting that the output is infected because it kind of looks like infected, right? But the actual is that it is not infected. So if I say 4001 now, now this is, we are doing this correctly because this is 9.99. So probability that we are going to predict that this is not infected is higher. Okay, so seems like we are doing pretty good on the classification task. I hope you got a sense of how we went about approaching this problem. If there are any other questions, please do let me know. So yeah, if the question is, if we start the training process again, we'll start off with 97% accuracy because you are not recompiling the model, right? When you say fit again, the weights are always there. So that is something useful that take away, that if you start training your network from a pre-trained set of weights. So a lot of people also train the weights which have been trained by the other classic networks like ResNet, other networks that we saw, ResNet, VGGNet, GoogleNet. If you take weights from there as well and then start training your network, you will learn much more faster rather than starting off from random weights. Okay, for any classification task, it could be malaria detection, whereas that network is trained on classifying cats versus dogs. Even still, that is better than starting off with random weights. Okay. All right, so thanks again for coming. I hope you guys enjoyed this session and you were able to get something meaningful out of it. I'll see you next time. We'll